All right, let's push deeper into the concept of rendering in games, exploring some nuances and technical grit that might not come up in a surface-level explanation. Rendering in games isn't just about slapping visuals on your screen. It's a balancing act of art, physics, and computational wizardry, all happening under insane time constraints. Here's a harder look. Unlike movies, where a single frame might take hours to render, think Pixar films, games have to render each frame in milliseconds. 16.6 milliseconds for 60 frames per second, 8.3 milliseconds for 120 frames per second. This forces developers to cheat reality. They use approximations like level of detail, LOD. Distant objects get simpler models and lower res textures to save processing power. Culling stuff you can't see, like behind walls or outside your field of view, isn't rendered at all. Techniques like frustum culling or occlusion culling are key here. Baked lighting. Instead of calculating light bounce in real time, some games pre-compute lighting into static textures, like shadows on a wall, to fake realism without the cost. Rendering leans heavily on linear algebra. A three-dimensional object's vertices, or points in space, are stored as coordinates, x, y, z. These get transformed via matrices. Model matrix positions and orients the object in the game world. View matrix adjusts everything based on your camera, where you're looking from. Projection matrix flattens three-dimensional space into two-dimensional for your screen, adding perspective, near things big, far things small. The GPU crunches these transformations for millions of vertices per frame, then fills in the gaps with shaders, tiny programs that decide how each pixel looks based on texture, light, and material properties. Think of shaders as mini-artists. There are two main types. Vertex shaders handle the shape and position of objects. Fragment, or pixel, shaders color in the pixels, adding effects like metallic sheen or water ripples. For instance, in The Witcher 3, the wind-swaying grass isn't just animation. It's a shader tweaking vertex positions in real time based on a wind algorithm. Most games historically use rasterization, which we described earlier. It's fast but fakes a lot, like reflections being pre-baked screen space tricks. Ray tracing, on the other hand, is newer and heavier. It simulates light rays bouncing off surfaces for hyper-realistic reflections, shadows, and refractions. Think of Minecraft with RTX OnLight streaming through stained glass, casting colored glows. But it's a beast. Only high-end GPUs or clever upscaling like DLSS can handle it at decent FPS. Game engines like Unreal or Unity orchestrate this chaos. They juggle rendering with physics, AI, and input handling. Unreal's Nanite, for example, ditches traditional polygon limits by rendering micropolygons dynamically, letting developers cram insane detail into scenes without manually tweaking LODs. Ever seen a game stutter or textures pop in late? That's rendering hiccups. VRAM overload happens when too many high-res textures overwhelm your GPU's memory. Draw calls are another issue. Every object rendered needs a call to the GPU. Too many, say, a forest with 10,000 trees, choke the system unless batched or instanced. Shader complexity can also tank performance if not optimized, especially with overly fancy effects like volumetric fog. Rendering isn't just visual. Audio rendering or spatial sound and even physics like collision meshes tie into the pipeline indirectly. A game like Half-Life. Alex renders VR frames twice, one per eye, at 90+ FPS, syncing visuals with head tracking. Miss a frame and you're puking from motion sickness. So, rendering in games is less draw pretty picture and more solve a million tiny math problems while the clock's ticking. And don't screw up. Want me to zero in on a specific angle? Like how developers optimize this mess or what ray tracing's really doing under the hood?